Hello and welcome to the next installment of Engineering Fluid Mechanics. The topic of this and subsequent videos sort of associated with Lesson 23 is boundary layers. Gosh, I can't tell if that's in focus. Autofocus is acting up right now. Boundary layer theories and application, essentially Chapter 9 of our textbook. And let's start with something around page 326, 327. And on that page it discusses a type of flow called Colet Flow. Not sure the actual pronunciation. And essentially we have two parallel plates as being depicted here. And they're a distance apart of L. And Colet flow is characterized by the upper plate is being moved with a velocity of u, and it creates a velocity profile that is linear across the two plates. So that is, this point is moving in the fluid at a speed of almost u, and this point is moving at a speed of almost 0. And of course we have a no-slip condition here and here. In this flow, we would find that if we look at the velocity profile, that the shear stress tau is equal to the viscosity mu times the speed of the upper plate divided by the distance apart. We did a similar analysis back in Chapter 3. Now, a second type of flow would be the two plates, parallel plates, Helly-Shaw. So we still have two parallel plates. This time they're not moving relative to one another, they're fixed. And we induce flow by forcing liquid onto one end of the plate, into the entrance, and capturing it at the exit. Generally the plates are B units apart. We'll measure Y upward from the bottom plate, and a flow profile in Helly-Shaw flow is the case where the velocity distribution across is described by a parabola. And S is the direction of flow. In this case, we find that the velocity distribution is well described by minus 1 over 2 times u, 2 times mu, the viscosity, By minus y squared, d by ds of P plus rho g z, or I guess rho gy in this diagram, and the average velocity is 2/3 times u max. Okay, so this is basically page 328 for the full details. And it turns out that Helly-Shaw is a good approximation for porous flow. It's generally pretty close to inviscid flow, and it has a properties of that. Now imagine these two cases where we cut everything in half. So instead of flow between two plates, we're going to have flow passing a single plate. And we'll look either on top or on bottom or on both sides of the plate. And that's going to introduce something that we call a boundary layer. So here's our first plate. It has a length L. Out here, some distance upstream of the plate, we have uniform velocity profile. Everything's all nice and uniform. Those little arrows are all the same length, parallel to one another. And we'll call that velocity profile U. And this will be a low Reynolds number condition. And what we'll find when we get to the back side of the plate is we no longer have a uniform profile. No surprise there. But we have the velocity profile looks something like this. And we arbitrarily declare when we get to 0.99, let's call this U0, U approach. So when this profile gets back to 99% of the approach, we call that that's how we define where the boundary layer is. And if we were moving these lines along the plate, it might do something like this. We'll bring back the simulator on the cell phone because that's something that we can represent in that simulation quite nicely. So this is a case where the Reynolds number based on L is around 10. So features that are important: it extends forward of the plate. So the disturbance is actually pushed in front of the plate. The distance of these disturbances are somewhat proportional to where we are on the plate. So as the plate gets longer, that distance, at least at the end, gets quite a bit larger, and this area is called the viscous displacements. And generally the whole region here, which is going to be shaded in green, is the boundary layer. Outside the boundary layer, inviscid flow is a good explanation. So it behaves as if it's inviscid flow until it reaches this little bit, till the presence of the plate is felt by the fluid. There's a viscous displacement zone, or we'll call it a boundary layer. That viscous displacement zone forms this disturbance, but outside of it, the flow still behaves as if it were inviscid flow. If we play the same game, but now go to a much higher Reynolds number, the plate hasn't changed. My ability to draw it certainly has, but the plate hasn't changed. So the plate still has a length L. The approach velocities are going to be much bigger. And what happens here is, because of the high Reynolds number, the extension forward of the plate is barely detectable. And we have this region forming, which is called a laminar boundary layer. We get to a point somewhere along the plate where we're back to 0.99 approach, 0.99 approach, and the boundary layer changes form and becomes something called a turbulent boundary layer. And when we get to the end of the plate, we have a quite a bit different looking profile than before. And I'm just arbitrarily sketching it. There we go. Ignore that line right there. We get a very logarithmic looking profile. Here we have a very parabolic looking profile. In this region right here, we'll have the very parabolic looking profile. Okay, what I can't draw is the length of these vectors is supposed to be the same. Okay, here we have a turbulent boundary layer. In this laminar portion, the displacement distance or the thickness is quite a bit smaller than the overall length of the object, and when we get out to the turbulent, we have different behavior there too. Okay, so things that are important from a fluid mechanics perspective is how thick the boundary layer is, and of course the resistance to flow caused by that. In the turbulent case is where the breakaway occurs, where it goes from laminar to turbulent, because if we can impact where that occurs, we can again change the associated resistance forces to flow. Okay, so this one is for a higher Reynolds number, and I have no particular numerical value of what the Reynolds number in that case is. Maybe 2,000 or 3,000. All right, there was a researcher a long time ago named Blasi, noted for his cigarette smoking capability, among other things. Not really, I have no idea if he smoked cigarettes. But he had an approximation for the boundary layer thickness. Or he discovered, or is attributed with discovering an approximation for the boundary layer. And that thickness is what I've been calling delta. So imagine our plate again. Here's delta. We're now going to measure x from the leading edge. And we have some approach velocity. So Blasi studied these, and a lot of subsequent researchers studied them. And they came up with the following approximations. In laminar flow, the disturbance height of layer thickness is equal to 5 times the value of x divided by the Reynolds number based on x to the 1/2 power. Now this key is important. Reynolds number on x, it changes value as we move to different locations on the plate. And this is valid for the Reynolds number dependent on x of less than 1,000,000. And it's the turbulent correlation, or the turbulent model, is that the thickness is equal to 0.16 x divided by Reynolds number based on x to the 1/7 power. And this is valid for Reynolds numbers based on x of greater than 10 to the 6th. So let's examine one way of using this information. we care what the boundary layer thickness is in some sense because the drag force and lift force, for that matter, that we've already studied changes based on the boundary layer thickness and the type of boundary layer. Okay, so let's suppose we have the following flat plate, and we are interested, we have an approach velocity of 20 feet per second. The fluid viscosity is 1.09 times 10 to the minus fifth feet squared per second. It pretty much puts us in a water type viscosity. We measure x along the plate to some location, and we're interested in how large is x when the boundary layer equals 1 inch, which is equal to 1/12 of a foot. Okay, so here's our known delta equals 1/12 foot. X is equal to what value? Where does that occur? Well, the way to proceed is we're going to assume laminar, and we'll discover if that assumption is incorrect. The calculations will tell us that. The Reynolds number based on the characteristic size x is equal to the velocity times x divided by the viscosity. In our case, the velocity over the viscosity is 20 feet per second divided by 1.09 times 10 to the minus fifth feet squared per second, which equals 1.84 times 10 to the sixth per foot. So that number multiplied by x produces a Reynolds number. Next, we'll use the Blasi-Laminar formula. So the thickness is equal to 5 times x divided by square root of 1.84 times 10 to the sixth times x in feet. And we set this equal to 1/12. Okay, if we do that, we have 1/12 quantity squared equals 25x squared over 1.84 times 10 to the sixth times x. That x and the square cancel. And solving for x, we have x is equal to 1.84 times 10 to the sixth times 1/12 quantity squared divided by 25, which is equal to 511 feet. Now we need to check the Reynolds number. We put 511 feet into the Reynolds number of x formula. We have Reynolds number on x is equal to 1.84 times 10 to the sixth times 511 feet, which produces a value of 9.4 times 10 to the eighth, which is bigger than 10 to the sixth, therefore not laminar. So we use the turbulent model, which is in our book equation 9.33. So Continuing on with the analysis, the turbulent model says that the layer height is 0.16 times x divided by the Reynolds number based on x to the 1/7 power. So that's 0.16 x over 1.84 times 10 to the 6th x to the 1/7 power. Therefore, thickness to the 7th power is 0.16 to the 7th power x to the 7th power divided by 1.84 times 10 to the 6th x, which is equal to 0.16 to the 7th power x to the 6th power divided by 1.84 times 10 to the 6th. So now we want to solve for x. We have x to the 6th power is equal to thickness to the 7th power, 1.84 times 10 to the 6th power, divided by 0.16 raised to the 7th power. Solving for x, we have x is equal to thickness to the 7th, 1.84 times 10 to the 6th, divided by 0.16 to the 7th power, and all that is to the 1/6 power. Finally, we go ahead and put in numerical values. 1 over 12 to the 7th, 1.84 times 10 to the 6th, I guess a numerical value, 0.16 to the 7th power, raise the result of that arithmetic to the 1/6 power for a distance of 5.17 feet. Check the Reynolds number. Reynolds number on x is equal to 20. It's 5.17 divided by 1.09 times 10 to the minus 5th, which is 9.5 times 10 to the 6th, which is bigger than 1 times 10 to the 6th, therefore turbulent. And we're obviously screwed if we get between the two. So under the given conditions, the boundary layer equals 1 inch at 5.17 feet from the leading edge. Of the plate. All right. Next, we want to examine what's the point of this boundary layer at all. Well, we'll go ahead and sketch it again. Let's suppose we have a plate that looks like that, and here's our boundary layer. We know that this is 0.99 U0, and we now have formulas to estimate the thickness. So the utility of the boundary layer is estimating shear force on the plate, or at least the top side of the plate. Remember, there's an equal and opposite one on the bottom. Once the shear force is known, drag from the plate is easily approximated. This is used to guide experiments and forcing layer transition to control or reduce drag. The interest in a boundary layer, if you remember that shear is going to be roughly approximated by the viscosity times U0 over delta. If we produce a laminar boundary layer, at least at the high Reynolds numbers, delta is kind of small, so it comes up with some shear stress. When we multiply the shear stress by an area, we get a shear force and consequently on into friction. But the turbulent layers are quite a bit thicker, so D is a bigger number. And by making that a bigger number, U0 divided by a bigger number is a smaller number multiplied into the viscosity produces a smaller shear stress, and the lower shear stress leads to a lower drag. So a lot of times we want to trip that laminar layer and force it into turbulence. Let's see if I can go back to my sketch. Where'd my sketch go? So out here is the 99% line, and up on this leading edge, because it's pretty thin, there'd be more drag than the equivalent part in the turbulent zone because of the increased thickness. So if we can move the location where this transition occurs forward, and actually it'd be nice if we could get it to as far forward as possible on the plate, then because the turbulent layer is a little thicker, all other things being the same, we can experience a reduced apparent shear stress. Okay, so there's a dimensionless relationship that says that the coefficient of shear force, or we can come up with a relationship that C sub F is equal to the shear force divided by the area times rho U0 squared over 2 is the dimensionless relationship. And then these coefficients are 1.33 over Reynolds number x to the 1/2 power for laminar, and 0.032 over Reynolds number on x to the 1/2 power for Reynolds number less than 10 to the 7th. And for bigger Reynolds numbers, we get 0.523 times the natural log squared of 0.06 Reynolds number on x. So there's no firm single model that explains these shear coefficients as Reynolds number changes. Just looking at the difference between the laminar case and the transitional case, so it's starting to trip, we can see that the coefficient is almost an order of magnitude, 2 orders of magnitude smaller at higher Reynolds numbers because of the turbulent effect, and then smaller still in this other case. Okay, so let's imagine an entire plate, and we'll go ahead and calculate the drag on one side of a plate. And I hope that this should explain why I actually introduced drag before we introduce boundary layers. Made more sense to me. So let's imagine, if you will, we have a rectangular plate, 1 meter on this side, 3 meters wide, and it's passing through a fluid so that the apparent velocity of the fluid on this center line is 2 meters per second. So a boundary layer forms. We'll do it in red. And we're interested in what the height of the boundary layer is at the trailing edge. Okay, we'll presume that the fluid given has a density of 1.23 kilograms per meter cubed and a viscosity of 1.46 times 10 to the minus fifth meters squared per second. Based on that density and viscosity, we're probably in air. And we want to find the value of the boundary layer thickness at the trailing edge, and then estimate drag force on the top of the plate. So we'll start out with calculating a Reynolds number based on the length. The length we have is going to be 1 meter. The approach velocity is 2, so we have 2.0 meters per second. 1.0 meters divided by 1.45 times 10 to the minus fifth meters squared seconds, which equals 137,000. Less than 10 to the sixth, probably laminar. We'll use our coefficient of friction relationship, which says that for laminar, 1.33, Reynolds number on x to the 1/2 power. So this is equal to 1.33, 137,000 to the 1/2 power equals 0.0036. Therefore, the shear force expected is going to be coefficient of shear, area over which it's applied, rho u0 squared over 2. This equals 0.0036. Our area is 3 meters by 1 meters. Our rho is 1.23 kilograms per meters cubed. Meters. We have a velocity of 2 meters per second. It's squared. And see that area density all divided by 2, which is 0.0265 newtons is the shear force on the plate. Next, let's go ahead and find the layer thickness at the trailing edge. It's going to be 5 times the distance divided by Reynolds number based on that distance to the 1/2 power. That's the Blasius relation. So it's 5 times 1 over 137,000 to the 1/2 power, which equals 0.0135 meters, 13.5 millimeters. About a 1/2 inch. Okay, to do it into U.S. customary. Okay, so that's an application of the principles of boundary layers. Now, obviously, Chapter 9 is much more elaborate than just what I've done here, but this is sufficient to allow you to handle quite a bit of problems in Chapter 9, or some fairly elementary boundary layer problems if you encounter them in your career.
that concludes this video. The next video will be some selected problems involving boundary layer theory.